Right now, at this very moment, our planet is moving faster than it does at any other time of the year. You cannot feel it, you cannot hear it. There is no shift in the sky, no vibration in the ground, and no sign in the air. Yet the Earth is accelerating as it travels through space. This happens quietly, every January, when our planet reaches a point in its orbit that changes everything about its speed. The question is simple: how fast are we moving right now? We often imagine Earth as still, resting beneath our feet. But nothing about this planet is static. Earth rotates, completing one full turn every 24 hours. Earth orbits the Sun, sweeping one full loop every year. And the entire solar system itself races through the Milky Way at unimaginable speed. But what most people never learn is that Earth's orbital speed is not constant. It changes throughout the year, increasing and decreasing in response to where we are along our elliptical path around the Sun. And right now, at the start of January, Earth reaches its maximum speed. To understand why, we return to the basic rules that govern every planet in the solar system. More than 400 years ago, Johannes Kepler discovered that planets do not orbit at a constant pace. Instead, they move faster when they are closer to the Sun and slower when they are farther away. This is Kepler's second law, the law of equal areas, and it explains the rhythm of Earth's annual acceleration. In early January, during a moment called perihelion, Earth reaches its closest point to the Sun, and because of that, the planet speeds up. The numbers are staggering. At perihelion, Earth moves at approximately 30.29 kilometers per second. That is more than 108,000 kilometers per hour, 6 times faster than a spacecraft leaving Earth's atmosphere, 1,000 times faster than a jet, and nearly 100,000 times faster than the speed of a rifle bullet. In July, when Earth is farthest from the Sun, our speed slows by more than a full kilometer per second. A difference large enough to reshape the timing of the seasons, yet subtle enough that we never feel it. The obvious question is, if Earth is accelerating, why don't we notice anything? The answer is that everything around us, the oceans, the continents, the air, and our bodies, is accelerating at exactly the same pace. There is no jolt, no force pushing us sideways, no sudden pressure on the ground. Orbital acceleration is not like the acceleration of a car or an aircraft. It does not create a sensation because it is uniform across the entire surface of the planet. We are not separate from the motion. We are part of it. Even though we cannot feel this acceleration, its effects shape the structure of the year. Because Earth moves faster at perihelion, the portion of the year around January passes more quickly. In the northern hemisphere, this means winter is slightly shorter than summer. In the southern hemisphere, it means summer is shorter but more intense. These differences in seasonal length are small but measurable. The shape of Earth's orbit, not the tilt of its axis, determines how long each season lasts. And the changing speed of our planet is the reason why. Earth's changing orbital speed also plays a role in how the planet distributes energy. In January, the northern hemisphere is tilted away from the Sun, keeping temperatures low despite the increased speed and closeness to the Sun. Meanwhile, the southern hemisphere absorbs more energy because it is tilted toward the Sun and is mostly covered in ocean, which stores heat more effectively. The result is a complex dance of sunlight, orbit, and axial tilt. January becomes the moment when Earth has the greatest imbalance between incoming and outgoing energy. The planet loses heat faster than at any other time of the year. This acceleration also matters beyond the surface. Satellites orbiting Earth must account for the planet's changing speed. Precise navigation, satellite tracking, and space mission planning all rely on models that incorporate Earth's variable orbital velocity. Even the drag experienced by satellites in low Earth orbit changes slightly due to seasonal variations in atmospheric density, a phenomenon linked to how Earth absorbs and releases heat during this high-speed portion of its orbit. The changes are subtle, but in spaceflight, subtle is everything. On longer timescales, Earth's orbital shape, and therefore its speed, changes due to gravitational interactions with other planets. These long cycles, known as Milankovitch cycles, influence climate over tens of thousands of years. Small variations in orbital speed affect how sunlight is distributed across the globe, contributing to ice ages and interglacial periods. The acceleration we experience each January is part of a much larger pattern, one that has shaped Earth's climate for millions of years and will continue to do so long after us. If Earth's orbit were to change more dramatically, if the shape became more stretched, or the distance to the sun varied more sharply, the seasonal contrasts would intensify. Winters would become colder, summers hotter, and the timing of energy distribution across the planet would shift. If Earth's orbit were perfectly circular, the speed would remain nearly constant, and the seasons would become more even, less extreme, and more predictable. These are not hypothetical fantasies. They are direct consequences of orbital mechanics. And so, in these early days of January, the planet moves faster than usual, accelerating silently through space. There is no sign of this motion in the morning sky. No indication on the horizon. Nothing in the air to tell us that we are now traveling at more than 30 kilometers per second. But the motion is real. It shapes our seasons. It influences our climate. It affects our satellites. And it reminds us that even in the calmest moments of life on Earth, we are passengers on a world that never stops moving, changing speed, changing distance, and changing the path of time itself as it circles the sun.